Hi there. Right, this is about the shapes of molecules with 5 electron sets around the central atom. So here we have the total number of electron sets around the central atom, and in this column we have the number of those sets which are bonding sets, and the combination of those two things determines the shape. I've only got 4 shapes here, although there should be another one where we have 5 bonding sets but only 5 electron sets, but only 1 bonding set. But that, of course, would be linear anyway. So with 5 electron sets, 5 of them bonding, this is the first level 3 shape is trigonal bipyramid. And we have the central atom here. We have 5 electron sets around that central atom, and we have 5 of them are bonding. And it's called a trigonal bipyramid because that molecule would fit into a shape like this. This is basically 2 triangular-based pyramids, or tetrahedrons if you like, joined together along one face. So it's actually got 6 sides. I guess it's a hexahedron, this one, than a tetrahedron. And the molecule, the trigonal bipyramid, should fit inside there. And that is why it has that shape. Okay, so we actually pull this apart a little bit. We can see that in there we can actually see the central atom, and we can see 1, 2, 3, 4 of the outer atoms, and the 5th outer atom is down there. The electron sets, of course, are the toothpicks, and if this will come out without falling to bits, so I don't know whether we saw that before. Central atom, 4 outer atoms there, and the 5th outer atom there. Now, we also have a very strange thing in this molecule because we have 2 different bond angles. Okay, when these things repel as far apart as they can get, we have some atoms that are what we call polar, this one and this one. They form a line straight through, so it's a little bit like the Earth. The poles are here, and around the middle of the Earth, what do we have? The equator. So these are sometimes called polar atoms or positions, and the ones around the middle are equatorial positions. The angle between the polar bond and the equatorial bond is 90 degrees. And if all these atoms are the same size, it is exactly 90 degrees. And that's 90 degrees from the southern pole to the equatorial. Between any polar atom and one of these equatorial atoms, the bond angle will be 90 degrees. But the angle between the equatorial bonds is 120. We've got 1, 2, 3 bonding pairs around there, and of course divide the circle by 3, we get 120 degrees. So you can see that the bond angle there is 120 degrees. And so down here we've got this showing these are the polar positions here, and then around the middle we have 1, 2, 3 equatorial positions. Okay, the next shape, 5 and 4 bonding pairs or sets, is called a seesaw. And here I've drawn supposedly a 3D diagram, but it's got a lone pair showing. So without the lone pair showing, I've tipped it on its side. You can see it's a little bit like a seesaw. If someone sits here, someone sits there, they could rock back and forth. Okay, and we still, in this example, have 2 bond angles. We still have an angle between the polar molecules and the equatorial molecules. We still have 2 bonds in the equatorial plane which have a bond angle of 120, and you can see we still have our 5 electron sets there. 1 non-bonding pair, 1, 2, 3, 4, 5 sets. You can see if I turned it up to sit on those equatorial atoms, it can rock back and forth like a seesaw, hence the name seesaw. I'll turn it around so we can see the bond angles. Right, moving right on, we have 5 electron sets with 3 bonding pairs, forms a T-shape. And here we have the T-shape because there is only 1 bonding pair in the equatorial plane there, we don't have the 120-degree bond angle because in the equatorial plane we have two non-bonding pairs and one bonding pair. We still have the two polar bonds and only one equatorial bond. The bond angle there is 90 degrees. However, in both this one, the seesaw, and the T, the extra push of those non-bonding pairs will actually distort those quite a lot. It will force those angles down below 90, and on this one both of those angles will be pushed closed a little bit by the by this non-bonding pair here. Then we get down to having, this has been sitting around overnight, it's gone out of shape a little bit. We have 5 electron pairs, but only 2 of them are bonding pairs, and we get this linear shape here with just the 2 polar position atoms still with us, and the 3 non-bonding pairs around the middle. If they will push nice and evenly, and the bond angle will be exactly 180 degrees because they will have the non-bonding pairs will push evenly on those. Examples here, this one here for the full bipyramid shape, PCl5, one of our favorite chlorinating agents from the organic topic, SF4 with S in the middle for fluorine atoms, ClF3 with chlorine in the middle, 3 fluorine atoms. Linear, we have a number of things. This I3 minus, surprising, is quite common. The I3 minus ion is the brown color in iodine solution because it's a mixture of iodine and iodide, and they form that brown species there. ICl2 minus, another ion, and XeF3, an actual molecule with xenon. And I think that about covers the things based on 5 electron sets. Thank you.